And today I would like to give a talk, which is kind of a mashup of a couple of things that I've done in during my PhD here at GFZ, together with Christoph Schoenfelder, whom you might know as well, who's quite involved in the ITN as well. This is about well, seismic interferometry or noise interferometry actually at volcanoes. And here in this beautiful background image, you can see the Klyuchevskoy group in Kamchatka. So this is an image that has been taken on the, or has been taken from the ISS. So this is this Klyuchevskoy group, well, as seen from space. We can see here Klyuchevskoy erupting at this moment. There are a bunch of other volcanoes around here. As I said, it's a volcanic group. So the actual volcanic group is only here, but there are Kamchatka is kind of really clustered with volcanoes. We have some others here, there, some in the north. We'll see that later in the map view a bit more clearly. And this is by no means, of course, not just my work, but this is really, well, a couple of people from different institutions have contributed to this. Well, first and foremost, of course, GFZ, but it's also some collaborators from the University of Washington, and well, here at Potsdam and Berlin, and then Alec Yates, which I actually haven't written on there, is from East Ham. Okay, so let's get started. My outline. I'm going to talk a little bit about theory. I think you should be familiar with most of the things I'm doing here. So this will be real quick. And then we're going to have a look at two applications, one of them being the Klyuchevskoy group, which we've just seen in the title slide. And the second will be amounts at Helens, which I guess also explains why University of Washington comes in at some point. And then I'm going to draw some conclusions from these two examples. And, well, we'll basically try to discuss what is similar, what is different, what are my experiences with passive image interferometry at volcanoes. So let's get into the theory. So this is an image I like to use. Unfortunately, I'm not quite sure who actually created this, but it's coming from somewhere in Grenoble. This basically shows the situation of two seismic stations located somewhere in space, or at the surface mostly, are recording nothing, or actually more precisely recording noise. So we have this background noise recorded at both stations that we see here. I don't know if you can see my mouse pointer at all, or if I'm just wheeling around with a pointer pointlessly.
We can see it.
Great, thank you. And we have the other station also just recording some of these weird wiggles. Turns out this is not just noise by its definition, but this is actually signal as well. And we can obtain a coherent part of the signal by calculating a cross correlation between these two signals, and this is shown up here. In this sketch here, we can see something emerges, and there's sort of this bit where the amplitude of the correlation is a lot higher, and this is when the noise from station A has traveled to station B. So let's say after a lag time of 10 seconds, depending on the wave speed here, we get this ballistic arrival. We also get a coda, which is way smaller and which basically originates from this ambient noise that has been scattered and reflected back and forth within this plane, and of course also outside of this plane. And turns out what we see here is actually an approximation of the Green's function between the two stations. So this is an impulse response function between the two stations, and this is not the entire truth though, but I'm going to talk about that in a bit. So I said I want to look at changes. So in the situation we've seen right now, we had this one static Green's function, but of course what we can do now is we can go ahead and take the noise from 1 hour and compute a Green's function, and then compute another Green's function for the second hour, for the third hour, so on and so forth. And of course we can do that in any time delta that we really choose to do it for. So here I went ahead and computed this these exemplary Green's functions. This is somewhere in Nepal. I think this is a sequence after the Gorkha earthquake. Well, we have 20 days of these correlation functions of these empirical Green's functions. And if we now, well, have a really close look at these functions, we could see that they change ever so slightly from day to day. And there's especially if we look at these parts in the coda, and this turns out to be a velocity change in the medium. So how do we quantify this velocity change? What we can do, pardon me. What we can do is we can quantify this change by basically stretching the functions against each other, and this stretch would then be equivalent to a homogeneous velocity change. So we get a reference function, which for convenience sake can just be the average of all of these functions, and check how much each of these daily functions has to be stretched against its average function, and then well, -1 times this stretch is going to be the velocity change as written here. So that's a fairly simple algorithm to retrieve this change. And I do this with the software that I wrote. So there's a software specially targeted at passive image interferometry here. This is the link that will lead you to GitHub on the QR code. And there's also a paper that has been in review for quite a while now. So but it's also preprint available. So if you want to read about that, or ask me about that if you have questions. Again, I just set up. So this is strictly only valid if we were to actually retrieve Green's functions. Turns out we don't, because we never have a spatially and temporally uniform distribution of noise sources. So there are a couple of restrictions really that apply here, and this will become important later in the talk again, or very soon, I should say. So what are we actually looking at if we get one of these velocity change curves? So now, well, let's say we have retrieved a velocity change, but I mean, that's not really a physical, it's kind of a physical measure, of course, but we don't really know what we are actually physically looking at. But what we actually can see is we can see velocity drops due to earthquake damage. We can see these seasonal cycles here due to rainfall and freezing. I should be lying. Fabian's actually sitting here. Actually, I don't know if this is Fabian's figure. I think the Fabian's figure is below that. And we have groundwater fluctuations, volcanic deformation, which is mainly why I'm here right now. We see solar and lunar tides, we see thermal strain, thawing, freezing, we see a whole lot of things. And unfortunate as it is, we do often see them not separately, but together. And still the figures are kind of weird here. So we kind of have to go ahead and try and unravel all of these changes that kind of are messed up altogether, and then basically find out what we're looking at. Like the first thing we see is a velocity change curve, but we don't really know, is this going to be groundwater? Is this going to be rainwater? Is this going to be a glacier? Is this thermal strain? Whatever it is. So how do we do that? I try and illustrate this in these two examples that we're looking at right now. So first we have the Klyuchevskoy group and Kamchatka. This here is SPIN-ITN volcano. So this is one of the volcanoes in the Klyuchevskoy group, actually. And Kamchatka is up here. So in case you didn't know, we have the Pacific coast in the east. So we have the Pacific slab subducting under the Kamchatka peninsula. And this is why we get lots of these subduction volcanoes. So this is part of the, well, Pacific firing, if you want to call it like this. I think a lot of people don't like the term, but never mind. So everything I'm going to talk about in Kamchatka is already published, and there's a paper in JGR that was published earlier this year. So turns out, as I said, volcano is actually a really good example for these situations where DVOB, so velocity change, is influenced by a lot of different mechanisms. And it's not only that, it turns out it's also a really good example for non-stationary noise sources. Because, as an example for Kamchatka here, we have extremely active volcanoes who constantly emit these tremor noises. And as we can see in the spectrogram here already, we get these fluctuations in the energy. So we get these energy peaks, especially here above 1 Hertz. That will really make it quite tricky to compute a Green's function from this. And I'm illustrating this here. So I computed these correlation functions all over the year, and you can see that look extremely different. So we have the coda up here, and the coda is partly very strongly emphasized, and then no, not that strong on other places. And if I try and compute a velocity change from this using the algorithm I described before, I don't really get a stable curve. So I get this really messy curve that, well, doesn't really tell us anything other than that it didn't work. So why is that? As I see it, this is mainly because, well, we get noise sources that are really distributed quite differently. So as long as we would have 2 noise sources, or like very few noise sources that dominate the field but remain stable, we would have a Green's. We wouldn't retrieve the Green's function, but would more retrieve like a partly illuminated Green's function. So it wouldn't be a complete description of the ground impulse response, but just part description. But in this case, I think we get volcanoes which I'm sorry again, which emit really strong tremors and would illuminate the ground in at different places. And then we retrieve these correlation functions, which really describe completely different parts of the study region. So it wouldn't make any sense at all to like compare them with each other and stretch them against each other, which is why we get this awfully low stability here. So this low coherence was called, which is really just a correlation coefficient between this reference function that we're stretching against and the daily correlation functions that we look at here. I'm sorry, oh, geez, cold season. So in this case, what we did is we tried to find similar correlation functions. And we did this using this hierarchical clustering algorithm. And it turns out a lot of them are actually quite similar. So we get, for instance, this green part here, which seems to be one group according to this clustering algorithm. That again, that will be down here. So this is the part where we have fairly little volcanic activity, and it looks kind of similar on the spectrogram. It looks kind of similar on these correlation functions as well. So this seems to check out. And then during high volcanic activity, we get different clusters that activate, so maybe different volcanoes that are active. And also, if you just look at correlation functions, which are groups, so these are the different groups it found, or clusters. They look quite different against each other. So what I did now is I picked one of these time windows and applied the stretching algorithm to them. So I tried to calculate the velocity change for this part, for that part, and for some of the other small parts, just to see if that will work. And well, let's have a look at that right now. Luckily enough, it actually seems to work. So this is quite a busy figure. Sorry about that. First of all, I would like you to look at this scatter plot here, these little dots, which is just the velocity change. So this is given in percent here. The velocity drops downwards and velocity increases upwards. Well, and we can see there's some sort of dynamics here. Again, we don't really know what it is. We just look at it. So went ahead and plotted quite a few different measures here. These red vertical lines, these are earthquakes. So that would be a first point I listed in these, a number of points earlier. So here we could see whether there's maybe any earthquake damage. And as far as I'm concerned, I can't really see strong effects here. So maybe there's something. One could think that there is something that happens here, but if we have a really close look, we can see that the velocity actually drops before the origin time of the earthquake. So this is probably not due to earthquake damage. Then I also plotted the volcanic discharge rate. So this is the lava output of the closest volcano, Vesimiani. Volcano in blue, and of the Klyuchevskoy volcano in red, which both are constantly background erupting, but this is actually not a whole lot of the output here we look at. And we see it doesn't really change that much over time, so that probably doesn't impact this velocity change curve either. And then lastly, I looked at this at these simple meteorological measurements, one of them being the precipitation here in blue, and the other one just being the snow load. So basically the snow thickness on top of the soil. It turns out this actually has quite the impact on the velocity change. So if we look here, every time we get one of these strong precipitation events like here, we get a velocity drop. That's also the case here, and also the case there. But this competing effect that we get due to this snow load seems also to be a thing that is happening here. So we have the snow load that basically compacts the soil, increased overload pressure, increases the velocity. Whereas this increase in pore pressure, like this rainwater refill, is a competing effect that would decrease the velocity. So I tried to model this here with this dashed line curve. So this is the theoretical apparent velocity change just based on these two measures. This is simply least square fit. It's a fairly simple equation actually. So there's a bit of diffusion involved. So well, basically what I model is that we get a precipitation, and then there's a time afterwards where it will affect the pore pressure. So we basically have an exponential decay function afterwards. Plus we have the snow load here, which really is just a thickness times a constant, which is determined over least squared. And this actually, considering it's that simple, seems to fit quite well. So we can explain most of our data at this time with just these two simple measures. So far, so great. Right. Please wait here anyway. But if we have a look at a different time window, we can see other effects as well. So here we can see quite clearly that there's this strong magnitude 7.2 earthquake, which induces this strong velocity drop, or somewhat strong velocity drop at least, across several stations. So this is one thing you can see. You can also see actually the small earthquake here as an effect as well. Fortunately enough, we don't have too many weather changes here, so we don't have to deal with these effects and like think about what this might be as well. One thing that really interested me here actually is that this increasing trend that we see here, and this, well, we believe is due to volcanic inflation. So you can see we get this sort of this trend that probably is a recovery trend from the earthquake, but then suddenly some of these points take off, and now we will see that there are actually different markers that are used here. I used circles, and I used squares, and I used triangles, and these are different groups of stations. And the circles are the ones that are closest to Vesimiani volcano, which actually so happened to be erupting about a year after. And the triangles are the ones that are the furthest away. So we see there's sort of a trend that the circles are inflating stronger and or increasing stronger, whereas the triangles are not so much, to maybe not at all. And another way we try to we try to ensure ourselves what this might be is we had a look at satellite data. So this is synthetic arbitrator data where we can basically we get an image, we get a radar image, and we quantify the pixel offset within the image from time to time. So we get an image about every 2 weeks. And then we can see how many pixels are moved in the image. So we use an image correlation. And now this is the whole time series that I have. You can see it's fairly long, but it's also pretty coarse actually. And this red bit, so we have the two red vertical lines here. This is the velocity change time series that we look at. So this is the time window we just looked at. And again, if we go inside here, so this is basically a zoom of this part. We see there has been an increase, like a market increase or market pixel offset between 0.2 and 0.3. And this is also exactly the time when we see this strong velocity, sun velocity increase. But the only difference is instead of saying there was something in between these 2 weeks, we can actually put it down to about 2 hours accuracy. So this is quite nice. It seems to really to check out right now. And well, we see like this velocity increase, which is, I would say, due to volcanic inflation. All right, so let's move on to Makus and Helens. So we basically go to the other side of the world. A nice thing about Makus and Helens is there's a lot of data. And what you can see here, data is really there all the time. But it's the fact that there is a lot of data is actually also the bad thing, because the data has a really variable quality. So some of these stations are analog stations, which are really transmitted telemetrized, so they're analogically sent by a radio station, and then they're only digitized in Seattle, actually, which gives you quite a lot of funny noise. And well, as of 2018, really, they started to install a lot more digital broadband seismometers, and the data quality gets a lot better. Now, I went ahead and applied the whole algorithm again to the data from Makus and Helens, and received this velocity change curve, which is actually quite remarkable, mostly because of the amplitudes we're looking at here. So we see this like 3.5% increase over what 16 years at the summit of Makus and Helens, and that is actually quite a lot. So this is a very large amplitude increase. And well, of course, we have to go ahead and ask ourselves, why is that the case? How does this make sense? Can this be real, actually? We also see these typical seasonal cycles. So these peaks that we get in between here. These are really typical weather cycles. So we get, as I said, high snow load in the early spring. And then a lot of water input in early summer and late autumn, which really influence the velocity, especially in the shallow layers. So here for Makus and Helens, I've tried something different. Instead of just looking at these 1D curves, I tried to look at this velocity change on a map. So this works in the following way. Given we have two stations, we can compute one of these sensitivity kernels. So this is basically a measure of energy diffusion within a homogeneous medium. And you can imagine if we have two stations here and we measure velocity change between them, then this would basically give us the likelihood of where this velocity change is coming from, or how this velocity change is distributed in space. Of course, with two stations, it doesn't really tell us anything. Other than that, we have no sensitivity here, for example. But if we have now a bunch of stations, or a bunch of cross correlations, a bunch of these sensitivity kernels, we can combine them, and we can use them for an inversion in which we basically retrieve a velocity change map. So this here is forward problem where we have this 1D velocity change. So these are the velocity changes we just looked at between two stations. And we have a sensitivity kernel matrix, so matrix all of these kernels. And this times the model, so times the velocity change map, should that ideally give us the 1D velocity changes. Of course, this would be the idealized forward problem without any noise. But for the inversion, we would have to do a damped inversion at this point. Anyway, so we apply this. This is a scheme by Obermann et al. Actually, I don't know why I didn't write this here that I'm using. And this is what we receive. So here we look at the total velocity change on a map. Again, 0.5 to 1 hertz, so the same frequencies we looked at before. This tells us something about the depth we're looking at. Generally, higher frequencies, shallower depth, lower frequencies will be deeper depth, since it's fairly high frequency. And what we can see, we have these high velocity changes, and actually focused in this sort of bullseye structure left of the west of the volcano, pardon me. And again, we ask ourselves, where are these coming from? So we look at different data sets. Fortunately enough, the volcano, well, quite a lot of people are interested in measuring quite a lot of things. So there are a few GPS stations with on the volcano, and this is the closest one to this sort of bullseye. And we can see that there is this deflating trend, and that makes actually a lot of sense. There was quite a major eruption at Mount St. Helens between 2004 2008. And most of the output actually happened in early 2004. So this is when the volcano started to deflate. And with this deflation and with this cooling that accompanies the deflation, we would expect the seismic velocity to decrease as well. And this is what we're seeing. So this would probably check out. Secondly, considering the location of this blob here, of this velocity increase, I had a look at tomography here. So this is combined surface wave and local earthquake tomography actually. And as it turns out, this block here is right above the feeding magma chamber of Mount St. Helens. So if we have basically a deflating magma chamber, which would allow everything on top to settle a little bit, and basically the cracks to close, we would again expect positive velocity change. So far so good. And of course, this is only one frequency we look at here. And we can ask ourselves, what about other frequencies? And here indicated the approximate maximum sensitivity. So this is the depth below surface level. So we have the highest frequencies. This is what we just looked at. And this is an even lower frequency. And they all seem to agree. So there's not a huge difference between all of these. The main difference that I see is, for one, the amplitudes, which are higher at higher frequencies. Probably makes sense because we mostly will see more changes in non-compacted soil than we would see in the bedrock. And we can also see in these intermediate frequencies that we get sort of a more spread out block. So maybe if we have a changing velocity, we can imagine this to be some sort of a sphere or spherical shaped body. which we target more in the middle here than we do there or there. All right. So now we basically had a look at the total integral of the velocity changes, but we can also have a look at the different frequencies within this velocity change time series. So in this case, I high-pass filtered the velocity change time series we had a look at on the first slide, on the first Helens slide. And I try to quantify what these velocity changes are coming from, where these velocity changes are coming from. And I again did this by modeling. So this is a bit more of an advanced model than what I used in Kamchatka, and we have a longer time series. Also, it's going to be a bit more complex. So input parameters for these are the water influx, which is precipitation and the snowmelt, and again the overloading snow. So it's the same thing, but it's a different model. It's a bit more complex. This model takes into account the diffusivity, so permeability of the medium. It actually solves the pore pressure differences in depth. So you have to input data from, let's say, 10 years before to adjust the pore pressure, right? And then it will act as shown here. As we can see, it fits okay. It's not neither great nor terrible, I would say. So we can see that most of these short-term dynamics are probably fairly well explained just using weather data. And this, in this case, doesn't include any temperature data. So this is thermal stress is, of course, also an effect we could take into account. So far, so good. Probably mostly pore pressure and overloading or confining pressure can explain these short-term changes. But then, what about the long-term changes? So this is fairly fresh, and I'm actually not quite sure where I'm going here yet. So bear with me. What I try to do here is I wanted to have a look at these three velocity change curves. So we have three different frequencies. This is low frequent, intermediate frequency, high frequent. And then I figured that, well, we have the pore pressure changes maybe accounted for with this short-term changes, with this low period change, short period changes. That maybe this longer-term changes could be due to magma movement, and magma movement at volcanoes is often accompanied by smaller events. So what you see in the background here, this histogram, these are well, earthquakes above magnitude 0 appearing well below Mount St. Helens, really. So hard to tell, really. I mean, at some points, I feel these are actually modifying the velocity change, as for example here. So I think what you would expect is whenever there's magma movement, you would get a velocity change somehow. As there are pressure changes in the ground below, you might either expect a velocity drop or a velocity increase, depending on where the magma is going, basically. Again, whenever we get a cluster, at least at some points, I feel like we see some changes. For example, here we can see in the high frequencies we get an increase, whereas in the low frequencies we get a decrease. Could be the case. As well, for some of these trends, you might be able to observe that the lower frequencies might show a certain change a bit earlier than the higher frequencies. which would maybe make sense if you think about migrating magma probably mostly from the bottom to top. So, well, I realize this is an incomplete picture I'm looking at right now, so I tried and add another layer to it, which is the depth of each of these events we're looking at. So now at least we have one dimension more. And what I indicated here is the approximate sensitivity we have with all of these frequencies. So, well, black line, orange line, green line. So, for instance, this cluster of events here could probably well be interpreted as magma movement upwards. And this probably goes well within the sensitivity of all the frequencies. Whereas what we see here, so here we might wonder, why don't we see a change associated to this cluster of events? That's probably this cluster down here. But this won't really reach any sensitivities, or it won't really reach within the sensitivity of the ambient noise frequencies we're using here. Again, this is really recent. It's kind of hot off the press still. So yeah, I would actually kind of appreciate hearing any thoughts on this. Anyway, so this is where I'm at right now here. So my guess is that some of these like low frequent modulations of the velocity change at Mars and Helens might be associated to magma movement. Again, this is probably not the full picture. What I haven't told you yet, Mars and Helens is actually one of the few places that has a growing glacier on top of the mountain, which is because it was completely blown off during the 1980 eruption, and then it basically regrow in the 90s, and it's still it's still growing. So this is actually something that would as well have an increasing effect on the velocity as we increase overload onto the bedrock and the soil. So I wrote this kind of fuzzy conclusion, which is, surprise, as already what I showed in the introduction. The velocity change is really a composite measure, a complex measure at that. That consists of a lot of things, among them earthquake damage, weather effects, freezing, thawing, so on. We see tides, so we see solar and lunar tides, see volcanic deformation. We see a lot of things that we don't know where it's coming from, either because we don't have measures of this particular physical fact, or maybe even because we're not thinking about it yet. And at that, we don't understand physical models very well that link each of these parameters to the velocity change. So it's very difficult to isolate one of these effects and really quantify the change that came from one of the physical effects. So what we really need is also physical models explaining these relationships. Right. So there's that. That's what I leave you at right now, basically. Very satisfying, but as good as I could do so far. I have a bunch of resources here that, well, you might potentially be interested in. This is the Kamchatka paper that I showed earlier. Mount Helens, there's unfortunately nothing out yet. And this is a software paper to compute seismic velocity changes from ambient noise and do a whole lot more among this spatial imaging that I showed. There's a preprint available, and there's the software available as well. You can ask me about that anytime. All right, so that's it. Thank you very much.